Welcome to Theoretical Engineering. Today I'll be covering how to calculate the density of a gas using the ideal gas law. The ideal gas law states that PV equals nRT, P pressure, V volume, N number of moles, R the ideal gas constant, and T temperature. Rearranging this equation to find the molar density or the number of moles per meter cubed, we find N over V equals P over RT. Let's put this to one side for a moment and take a look at the relationship between mass and moles. The molecular weight is the mass of 1 mole. Molecular weight equals mass divided by moles. By rearranging this equation for moles, we can then substitute this into our ideal gas law. We can tidy this up by multiplying both sides of the equation by molecular weight. Now we have m over v equals p times molecular weight over r times t. The definition of density is mass divided by volume, and therefore we can substitute the left-hand side of our equation for density. Thus, the density of an ideal gas is pressure times molecular weight divided by the ideal gas constant times temperature. Be aware that this is only accurate for gases that are close to ideal conditions, ambient temperatures and pressures. An example of a close to ideal gas would be air at 20 degrees C and at atmospheric pressure. Air has an average molecular weight of 29 grams per mole and is made up of mainly nitrogen and oxygen. Plugging the numbers into our density equation with SI units, there's 10 to the 5 pascals of pressure, 29 times 10 to the minus 3 kilograms per mole of the molecular weight, 8.31, the ideal gas constant in joules per kilomole per Kelvin, and 293 Kelvin for temperature. Be careful that the units of the ideal gas constant and molecular weight line up. My tip would be to keep them both in kilograms. This gives an overall answer of 1.19 kilograms per meter cubed.